Welcome to the second part of Module 5 on genomic selection, where we're evaluating whether genomic selection is working, looking at research papers that evaluate the accuracy of genomic selection using Scheme 3. And here's one of those. We're looking at now the use of selection indices to improve stover and yield in U.S. maize. And here is our training population. They developed 223 F2 derived lines from a biparental cross, a single biparental cross. Each of these was crossed to a single tester to make test crosses. Each of these 223 test crosses were then evaluated for multiple traits at 4 environments. And using that data, they developed a selection index for stover and another selection index for yield plus stover. And they genotyped all these 223 inbred lines with 287 SNPs, and that is your training population. So that information is your training population in which you build your genomic selection model. From that, they selected the 10 best for each of the traits based on the phenotypes and intermated them 2 times to come up with the first cycle. And this first cycle then is generated by phenotypic selection. From that cycle, they looked at 192 lines, genotyped them, selected the 10 best for each of the 2 traits, and based on their estimated breeding values based on their genomic selection model, picked the 10 best and intermated them to form the second cycle. They repeated that step again, genotyped 192, selected the best based on genomic selection, and came up with the third cycle. They also looked at using marker-assisted selection, following the same scheme, selecting the best for each trait based solely on using marker-assisted selection. And that one, they used all the markers that were significant at a p-value less than 0.1. Went through the second cycle and then the third cycle. It gets a little more complicated when we look at how they're going to phenotype the selections. And I'll just go through one of these. Here they have quite a few selections in the cycle 3. They took 64 of them at random, created a bulk from them, and did a test cross of using the bulk of C2 plants as a bulk. So instead of testing 64 individual test crosses, they combined them and made one genotype that could be tested in the field. And they did that for stover index and then for yield index. They follow that same process in each of these, so they didn't have to field test 64 lines from each of these populations. And they were all field tested. Let's look at our results. This is for stover index alone. Cycle 0 is no selection. Stover index is not too good. You go through a cycle of phenotypic selection to get to cycle 1. The trait has improved based on phenotypic selection alone. Now you can go through genomic selection or marker-assisted selection. And if we follow the genomic selection, it has increased after one cycle of genomic selection. And you go through a second cycle of genomic selection, is increased further. Marker-assisted selection, the first cycle of that did not work too well, but you did a second cycle of marker-assisted selection and yield, the stover index did increase. But at that third cycle, genomic selection has produced a stover index that's 14% greater than what they got from marker-assisted selection. Now let's look at yield plus stover index. Again, cycle 0, no selection. It's not too good. Cycle of phenotypic selection, the trait has increased. A cycle of genomic selection or marker-assisted selection. Well, genomic selection, one cycle of genomic selection has increased that trait quite a bit. The second cycle of genomic selection did not do much. And here, marker-assisted selection did not increase the trait at all. So here, at our third cycle, genomic selection now has produced a trait values that are 50% greater than what you'd got with marker-assisted selection. So I think you certainly have to conclude here that marker-assisted selection, that genomic selection is working quite well. The last paper we're going to look at is also looking at Scheme 3, and this is looking at beta-glucan content in oats. In the training population, consists of 446 elite oat lines, and they term this the cycle 0. They're all phenotyped in cooperative trials over a long period of time, and this is probably, if I recall correctly, is an unbalanced historical data set that they used to build the training population on. And each of those 446 lines is genotyped with the SNPs. The selection scheme here gets very complicated, and I'm not going to go through this in any great detail. But here's your training population, cycle 0. And let's just go through part of this. You're going to take 12 parents selected based on their estimated breeding values from genomic selection. And there you're going to start going through cycles of genomic selection, and you're going to do it in 2 separate populations, 2 separate streams if you want to. And you go through these steps, one stream, and you go through another stream. And so each of these streams kind of acts as a replication of the ability of genomic selection to affect these traits. Following a very similar scheme, they're going to follow it now using only marker-assisted selection. And here the marker-assisted selection going through those steps is based on just 6 markers. And then they're going to do the same scheme, the same general idea again, but now doing phenotypic selection to get two outputs, 2 streams of lines produced from phenotypic selection. This information in this box are lines that are going to be phenotyped, and those are lines that result from 1 cycle of phenotypic selection, or 1 cycle of marker-assisted selection, or 1 cycle of genomic selection. The information down here is the lines that are produced by the 2nd cycle of each of these selection schemes. And let's look at the results. And again, this selection was looking at beta-glucan, and that's what's shown in this graph over here. So let's focus on that one. Cycle 0 is just your training population, and there is the average beta-glucan of those 446 lines. Now you've gone through one cycle of phenotypic selection, marker-assisted selection, or genomic selection. And all 3 of those schemes after 1 cycle produce progeny that are pretty much phenotypically equal. You go through the 2nd cycle of each of those schemes, and again you're producing progeny from each of them that are pretty much phenotypically equal. So what we conclude here is gains from phenotypic selection, marker-assisted selection, and genomic selection in this study for beta-glucan were equal, and that was the target trait. So there are changes in each of these populations and other traits that are correlated to beta-glucan, and I'm not going to discuss those results. But basically here, per cycle, gains from the 3 different selection schemes are equal. The authors do state, though, that they can go through 2 cycles of genomic selection in the time it takes to go 1 cycle of phenotypic selection. So here, per cycle, all 3 schemes are the same, but per unit of time, the genomic selection and the marker-assisted selection are superior. And really in this case, if you can get away with marker-assisted selection with 6 markers and get this kind of gain, probably the marker-assisted selection here is probably the best selection scheme. In summary, most published reports show that genomic selection does indeed work, whether you're using cross-validation scheme 1, scheme 2, or scheme 3, and that it can be a really effective and efficient complement to traditional plant breeding and marker-assisted selection. The reports show there are many ways to begin to implement genomic selection and show you quite a few different breeding schemes you can use. And the very important part is that in almost every one of these papers, genomic selection was implemented in current breeding populations of the breeders. In other words, the populations where you really most want to use it, and it's working in those populations. Also, quite a few of these papers show that training population sizes were often much smaller than what is recommended based on theory, and yet genomic selection still worked. And the advantages of genomic selection remain, as we talked about: low cost, reduced time to complete a cycle of selection. Here is a quiz on the information in Unit 5. Please feel free to take it or not. And if you do take it and want me to look at your answers, email them to me. Thank you for viewing this material, and as always, if you have questions, email them with me or Skype and we'll discuss them.